Hello and welcome to another interesting episode of the semiconductor webinar. We are live with Swastik Day. Swastik is MTech student in Institute of Radiophysics and Electronics in University of Calcutta. He is pursuing MTech, and today he will present on a topic on board development. Most of you have seen the Arduino board, the Raspberry Pi board, the RISC-V board. Now, where the chips reside in this board, one has to develop the board, and that is a very crucial part of making the usage of the chip for the end user. So, designing is something, and application of the design as an IoT or maybe some other embedded applications, we have to develop the board. So Swastik has done it by himself, and he will share first his journey through slides, and then he will move to the software for the technical nitty-gritties. So over to you, Swastik.
Yeah, sure. Thank you, sir. Uh, it's a great pleasure to finally be here and sharing the screen with you. Hi everyone. Just like Sir said, I am pursuing my master's from the Institute of Radiophysics and Electronics in the stream of VLSI designs. And my academic interests, they include systems ranging from embedded systems, Internet of Things, or FPGA based systems, and digital ASIC systems. So that is in even in what I'm doing my master's project as well. And today I have developed, not today, just a few time back, I have developed a project based on a PCB design of an RT board. So today I'm here to share it with every one of you. So without any further ado, let's start the presentation. So before we move on to why we should develop this board, let's see at some of the missing components that are present. There is a notion that everybody after completing their BTech, they usually try to join an IT industry. So I believe that this is a wrong mindset that has been somehow infused in our minds. Like people, they tend to think there is no such career scope or career opportunities in the electronics domain. Maybe different factors are playing over here. So lack of exposure to the EDA tools is one of the most important reasons why this mentality has been grown. Then there is also something that the developing VLSI industry. So right now we know that India is is growing very steadily in the world of VLSI, with different categories of chips that are coming out by the end of 2025. So I believe that is also one of the most important reasons why one should pursue their career in the VLSI department, or maybe in other departments like microelectronics and systems and all. And finally, we have something that happened in the past week, the Semicon India 2025. So this was the biggest VLSI meet in India that we saw. And most importantly, there are two particular chips that have been developed indigenously by the Institute of Radiophysics and Electronics. It is the C2S 0001. I think it's present over here, and the C2S 0048. So we can see that this is the different type of chips that have been manufactured in India indigenously by different agencies and all. And so I think, yeah, this pretty much sums up the reason why we should attend this webinar, and why one should pursue their career in the VLSI domain. So by the end of this webinar, we'll develop something like this. We'll see how to develop a PCB board like that in both software. And before we develop it, we will see how the different components work, what are the different components, some terminologies. So before anything, let's move on. Okay. So, being a electronic student, every one of us have heard about this particular term. Okay, this is called the microcontroller. So right from our bachelor days to still now, I'm still pursuing my MTech. So there is this thing called the microcontroller that is always buzzing around us. Now, what exactly is a microcontroller? So just like we can see, it has got a single integrated circuit and some built-in peripherals. Now, here three words are very important. Okay, so the first one is the single, the second one is the integrated, and the third one is the peripherals. Now, single is pretty much self-explanatory in nature. Everything is present on a single piece of silicon die. Next, there is this word that is the integrated. So what integrated basically means is that in an electronic circuit, there are different categories of peripherals that are present over there. They can be anything like analog to digital converters, or maybe counters, or timers, flip-flops. There are different categories of peripherals that are present. And all of these peripherals, these are all present on one single board. Okay, so this one single die, as we can see, when all of these different peripherals, when they are all put on a single board of silicon, then that resulting structure, that is what we call as a microcontroller. A microcontroller, unlike a microprocessor, has its own memory, and it is reprogrammable in nature. So yeah, we can do specific tasks from it, but we should always reprogram it to make it perform different categories of tasks. And now, to put it in a more real life perspective, if we can think that an IoT development board as a completely furnished car, then the microcontroller, this can be thought of as a complete engine with the different systems present in it. Like the braking system can be one of it, the gear system can be one of it, maybe the exhaust pipe system can be one of it. So an engine itself cannot perform anything much, but when it is associated with these different systems, it can make an entire car run smoothly. So microcontroller is somewhat similar to an engine with different subsystems associated with it. So let's move on to the next slide. A printed circuit board. Okay, so this printed circuit board, I think the picture is not coming properly over here for the Vero board. So this printed circuit board, this has been a buzzword for quite a long time. Uh, this is basically a board that holds different electronic components in it. Okay, so we have got various electronic components associated with it, and these are all soldered onto it. And this board consists of something. It is made up of called a material called a fiberglass material. It's a FR4 material. These boards, these are basically compact and efficient in nature, and these reduce the footprint of a complex circuit to a great extent. Now there can be a good classification like the different categories of printed circuit boards. Okay, so we'll see at two of those classifications. Before we move on, there is something that I would like to share, that before the PCB came into play, there was something called the Vero boards. Now, why the Vero boards weren't as much useful to us? It's because the first reason was Vero boards are extremely costly when we go for mass productions. Okay, so PCBs, they are very efficient when we go for mass productions, but Vero board is too much complicated and too much costly. And secondly, as circuits became more and more complex in nature, so Vero boards point to point connection between between different parts of a circuit became more and more increasingly complex, and this somewhere led to a degradation in the signal integrity. So people thought, okay, we are getting some sort of issues over here, let's switch to something called a printed circuit board. And this printed circuit board, I'll move on to the next slide now, sir. This printed circuit board, this can be categorized in different categories. There can be a flexible PCB. There can be these two types of PCBs, like a single layered and a multi-layered. So there are different categories of PCBs that we have. Today, we'll take a look at the very basic categorization, that is the number of layers a PCB has. So when a PCB was generally developed, it had something, it was a single layered PCB. Now, a single layered PCB can be compared to like a single storied building. Okay, sir. So, just like we have the ground floor, we can think of that single layered PCB, something like that. We have a copper foil over here. This copper foil is basically where all the electronic circuitry goes on. So all the components are assembled over there. Everything goes on and off over there. And on the right hand side, we can see that there is something called a multi-layered PCB. So a multi-layered PCB, we can again think of it as a multi-storied building. Just like different categories of tasks go on in a multi-storied building, different type of electronic circuitry operate in the different layers of a multi-layered PCB. Each of these layers are separated by something called the prefab layer, but that's a different story. And we'll also see how these different layers, how they communicate with each other shortly. So moving on to the next slide. Yeah, the types of components. Now, usually when we see a printed circuit board, there are usually two different categories of components that are present. One is the through hole components and the other one is the surface mounted components. This through hole components that we can see on the left hand side, this is basically they have something called these lead wires. So we can see that there are some pre-drilled holes in the PCB, and those lead legs, they just go into the pre-drilled holes, and and they are soldered from the other side. And for the surface mounted components, they also have lead legs coming out, but they are not drilled into the PCB. Rather, they sit on something called copper pads, and they are soldered on the same side of a PCB. Now, one important point of category is that this type of component that we see, the through hole components, this is generally called a DIP packaging. And the other thing that we see over here, this is called a quad flat packaging, a QFP type of packaging. If we move on to the next slide. Yeah. So some terminologies associated with PCBs. We have seen a PCB having different terms associated with them. The first one we will see is the silk screen layer. So just like we can see over here, this is a Raspberry Pi board on the backside of a Raspberry Pi board, and we can see that there are a lot of things printed in white color. So that entire layer that is printed in white color, that helps us to visualize what the pin is meant for, or what the different components are there for. That entire white colored layer, that is called a silk screen layer. Then there is something called the pads. So these are nothing but exposed copper areas on which the components are soldered. So just like we saw the QFP type of components, the SMD components, those components are soldered onto these pads. And then there is something called vias. So vias can be thought like we can think them to be very much similar to elevators in a multi-storied building. They basically helps you to conduct current from one layer to the other layer. There are three categories of vias that are usually associated with the PCB. The first one is the through hole components, the through hole vias, the buried vias, and the blind hole vias. So the through hole vias, they connect you from one end of the PCB to the other end, right? From one surface to the other surface. The buried vias, they take you anywhere in between the layers, right? Like from a second layer to a fourth layer, or maybe from a third layer to a second layer, something like that. And the blind hole vias, they take you from one of the surface to one of the intermediate layers. And that is how a multi-layered PCB works. So that is how different components in a multi-layered PCB receive the current, receive the data, and perform their function accordingly. Let's move on to the next slide. Okay, so that was all the terms that we needed to know about printed circuit board. Now let us see some important chips that we are going to use to design our board. The first one that we will see is the Atmega 328P chip. So this chip, this is developed by Atmel, and this is an 8-bit AVR microcontroller. Here This 8-bit basically means that the data bus of this particular microcontroller is 8-bit in nature. We can see the picture of an Atmega 328p on the right hand side, and on top we can see the same picture representation of the Atmega 328p in the software version. This Atmega 328p, this has something called the RISC architecture, the reduced instruction set computer architecture, and it has got a 32 kilobytes of in-system programmable flash. So we can reprogram this microcontroller, and we have got 32 kilobytes of flash memory for the reprogramming part. And out of these 32 kilobytes of flash memory, we have 0.5 kilobytes reserved for the bootloader. This microcontroller, this works in a voltage range of 1.8 volts to 5.5 volts, and we see that this microcontroller is basically or usually present in the Arduino boards. So since an Arduino operates on 5 volts, so this microcontroller is well within its operating voltage range. The P over here that we see in the Atmega 328P, this P basically stands for a low power consumption. So Atmel, what they had, Atmel developed Atmega 328 microcontroller in two different versions. The first one was the Atmega 328, and the second one was the low powered version, that is this, the Atmega 328P. If we move on to the next slide, in circuit serial programming headers. Okay, now we saw that the Atmega microcontroller, it had something called in system programming. This is exactly the same thing. The in circuit serial programming header pins, they help us to program the microcontroller. Okay, so this is a set of 6 pin connectors, and they work on serial peripheral interface, SPI based communication. This ISP header pins, these are basically used to program the microcontroller once it is placed on the circuit board. Until and unless we have a dedicated bootloader, the ICSP header pins are used to program our microcontroller once they are soldered onto the board. Now, this is another way of programming the microcontroller. We will see the actual method. This can be thought of as the backdoor to programming our microcontroller. We can use an external AVR programmer, maybe an external Arduino board or something else to program our Atmega 328P microcontroller. There are 6 different pins over here, and these are all male pins. We can see that the first one is the MISO pin, the master in slave output. Then we have the serial clock, the reset, the power pins, the MOSI pin, that is the master out slave in, and finally we have the ground pin. So that's the pin terminology of an ICSP header. If we go to the next slide, the CH340G chip. Okay, so as we can see that on the right hand side, the CH340 chip, this sits very close to the USB port of a microcontroller. What this CH340G chip does is that it converts data from USB protocol to a UART protocol. Now, why this is necessary? This is necessary because our microcontroller, the Atmega 328P that we saw, that speaks the language of UART protocol. And the PC that we are using to program our microcontroller, that speaks the language of the USB protocol. So somewhere somebody needs to be present to convert the data coming from the PC in USB protocol format to a UART protocol format. And that is exactly what is done by this CH340G chip. This converts the USB signals to a UART signals for the microcontroller. Of course, it requires a 12 megahertz crystal with capacitors. We will see the connection of the CH340G chip in our circuitry sometime later. And this particular chip, this can be found in Arduino clones. So you will not find this chip in the actual Arduino board, but you will find it very much in the Arduino clones. There is a reason why it is found in the Arduino clones. That is because the actual Arduino boards, they have something called the Atmega 16U2 as the converter chip, and CH340G is just basically a cheaper version of it. So whoever decided to design the clone of an Arduino, they thought that we'll use a cheaper version of the chip to design it. Okay, if we move on to the next slide, the mini USB serial bus. Right. So this mini USB serial bus, this is a entry point for everything in our circuit, be it data, be it the power, uh, data input or data output. Everything occurs from this mini USB serial bus. This USB serial bus, this has got 4 lines of communication, 2 for data and 2 for power and ground. We will see in the circuitry where these data lines are connected in a short while. And they of course they offer us a programming interface, and they works in serial communication with the microcontroller. And there's nothing much about this. Okay, so this is the finalized render of our entire circuitry. So before we move on to the next portion of our circuitry, there is something that we would like to summarize. So we saw 4 different kinds of terminologies. The first one was the Atmega 328P microcontroller. The second one was the ICSP header pins. The third one was the CH340G chip. And the fourth one was the mini USB bus that we saw. So now, if we put all of this in one single perspective, we can think that if we consider our entire IoT board as our house, then this mini USB that we saw just right now, that acts as the front door, while the CH340G, that acts as the doorman to our house. The Atmega 328P, that is basically the entire brain of the house, and the ICSP pin headers that we saw, they act as an emergency exit or the back door to the house. Now, keeping all of those in mind, this is the finalized render of our circuit that we will see. And we can see that there are different labelings that are present over here. So we have got the USB labeling connected over here, then some capacitors, these are connected. We have U2 as the CH340G chip. Then we have J1 over here that acts as the ICSP pin headers. And finally, we have U1 over here on the far right end that acts as the Atmega 328P microcontroller. We also have a reset button to reset our program in case something ever happens. In case our program gets stuck, so we always have a reset button. The reset button is very much synonymous to the restart button in our computers. Yeah, this is the 2-dimensional view of the finalized render that we saw, and this is a pretty much clearer version of what we saw over here. We can see the different types of capacitors that are present over there, the different resistors, the diode that is present over there, the X tile over here. This X tile is the clock that we are going to use, the reset button, and the different other chip circuitries that are present. And finally, if we go to the 3D render, then it looks something like this. So this is basically a 3-dimensional render of our entire circuitry. We have the USB circuitry over here, followed by the CH340G chip, and then we have the Atmega 328P microcontroller. Then over here we can see the J1 pins that acts as the ICSP header pins, and we also have the Xtal1, Xtal2 as 2 different clocks. Both of them are working at 12 megahertz. Finally, we have this LED to represent the presence of power, and we also have the reset button, just like we saw, to reset our microcontroller board. Okay, sir. So now I'll be sharing my screen, sir. Okay, sir. So how do I do it?
Let me remove it. Now you can again your from the sharing option. You can share your screen and I'll add it to stage.
Okay, sir.
Yeah. So just a minute. This is your, sorry, let me remove it. And uh, I think
Okay.
now you minimize this window and share your PCB tool. So minimize
Sure,
this.
sir.
Yeah,
Sure, sir.
yeah.
Okay, everyone. So this is what the entire circuitry looks like. This is what everything that we talked about, this is what it looks like in the real view. So we can see that we have the Atmega 328P microcontroller present over here. This is the ICSP header circuitry that we can see. Then we have the CH340G circuitry. I explained these. And finally, we have the USB circuitry. So let's start with this USB circuitry. We can see that we have a diode present over here, followed by some capacitors. These capacitors, they basically help in removing the DC noise and whatsoever. And just like I said, this USB, it works with this data. It has got two pins for power and two pins for data. So yeah, we have this data minus and data plus pins for the serial communication to the data. And we have this power pins, one for power and one for the ground. Now we know that the pins for USB circuitry, they head over to CH340G chip. So we can see the D minus and D plus pins. These are present right over here in this CH340G circuitry chip. Like the CH340G chip works in converts the data from USB protocol to UART protocol. So these D plus and D minus pins are finally converted to this USB RX and USB TX. So these are the UART pins that are coming out of the CH340G circuitry. Of course, we have got different other peripherals over here. This entire circuitry, this has been taken from the data sheets present that has been available. And just like we said, the CH340G circuitry, this works with the 12 megahertz clock over here. So yeah, we have the clock over here along with some capacitors. This is the ICSP header circuitry, the 6 different pins that we talked about. We have the MISO, clock and reset, followed by the power, MOSI and the ground pins. This ICSP header circuitry acts as a backdoor to our programming the microcontroller. And finally, we have a big circuit over here. This is the Atmega 328P microcontroller. So we see that the USB RX and USB TX pins that were coming out of the CH340G circuitry, you can see that they are present inside over here. So whatever data comes out from one of those pins is coming into these pins over here. There is this reset button that we were talking about. We can see this reset button over here. This is the power LED that we are talked about, and yeah, this is pretty much everything. So MISO and MOSI pins of the ICSP header circuitry, they are connected to the microcontroller as well for a backend communication in case the bootloader gets damaged somehow. This looks like pretty much the entire circuitry over here. This entire circuitry once again has been taken from the data sheets that are available. We saw the data sheets links over in the PDF as well. So now this was a circuitry schematic diagram, and that is the finalized render that we saw. So the different chips or components are present over there. So we have this as we can see this U1. This is the Atmega microcontroller that we talked about. Then we have this Xtal one as the different clock. Then the CH340G circuitry, the J1 as the ICSP header pins, and finally we have the USB over here. So I think that this is the finalized render of our entire PCB diagram. We also need to design the copper area, which is this entire bright red colored area that we are seeing. This copper area, this basically helps in grounding of the components, so we should design them accordingly. And now let us take a look at the 2D and the 3D view of the circuit. So if we go over here, by the way, this is the easy EDS software that I am using. It's a completely free to use software. Anybody can go to their web browser and just type in easy EDA, create a workspace, and you can start designing your own PCBs if you have. One point of note, the easy EDA has made the pro version free for everyone, so doesn't matter wherever you are watching this from, you can use the pro version. I have designed this in the standardized version because I think that's a little bit easier for me to use. Right. So if we see the two-dimensional view, we can just go over here and click on the 2D view. So we can see the two-dimensional view of the circuitry that is present over here. This is what we saw in the back in the slides available. We can see the different types of copper routing that is present, and just like we talked about the different VRs, so yeah, these are the different types of VRs that are available over here. This PCB of course is a two-layered PCB, that is why there are VRs available. And if we want to see the three-dimensional render of the circuit, we go back to the PCB view and we click on this 3D view option over here. It takes a while and there it is. So we can see, we can move around this entire PCB board to see how exactly it looks like in real time. This is the reset button over here. This is the power LED, a bunch of capacitors to the right end. Then we have the U1 circuitry, like we all talked about, the different types of circuitry that was available to us. We can just see how it looks like from the front and the back. We can see the different VRs that are available over here as well. That is the entire circuitry. That's how it looks like. And if you want to develop this printed circuit board in your own, we can always download the BOM files and the Gerber files. We can of course go over here, this icon over here, to click on it, and we can find the bill of materials that are present over here. So by clicking on this export BOM, we can generate our bill of material files, and of course we can always contact with a PC manufacturer to provide them with this file. And for the Gerber files, we need to click over here. So there is something called this DRC. This is a design rule check. This basically helps in checking out whether the entire design is made in accordance with some rules. So we can always check the DRC, and it takes a while to do the entire checking. Now before we generate the Gerber file, to the left hand side we can see that DRC errors are 0. So it means that there are no DRC errors available over here. And we can always download this entire Gerber file from over here. PCB quantity 5, we can change the color of the PCB. It doesn't matter. It's looking over blue over here, but based on this color our PCB will come out. It may be green, it may be blue, doesn't matter if. And we can have a Gerber view of this file over here. This is the easy EDA version of the same file. So yeah, that is pretty much all about it. I would suggest everyone to take a look at this easy EDA software and how to use it. And I would recommend each and every one of us watching this to go and design their entire PCB in this particular software. Also, there are different types of PCB vendors that are available. We can go in for Robu, that is one big PCB manufacturer that is available in India. JLC PCB, or maybe PCB Way, IPCB. There are different categories of PCB vendors. We can connect to any one of them. We can upload our Gerber files for a certain amount of money. We can get our PCB, and we can always explore with whatever we have designed. So yes sir, that was all about me.
So great, Swastik, and I would suggest that today's journey was a different one, because today, in the scenario of the semiconductor movement in the Indian territory, right, people are moving towards making the chips now.
Yes.
Now after that the chip has been made, it has to land on a board.
Yes, definitely.
Yes, so today we move a one step ahead after making the chips. It's always great to have the good chips, great chips, and excellent and fabulous chips.
Yes, sir.
And after that, we have to anyhow design a board
Yes.
to use that chip. So that is a very, very different journey today our audience had, because in the semiconductor webinar, we promote peer learning. As a student, you are sharing with the students, so they will learn from you, they will get encouraged, and they will have the belief that if he can, we can. So that
Yes,
is the
definitely.
message. That is the message through the semiconductor webinar. And this is our show, our domain, in our niche domain of the electronics, microelectronics, VLSI, embedded systems. Nowadays, everything is interconnected. That means if I am doing something, somewhere else in the entire ecosystem, there is some complementary part of it is there. So the complementary part of a chip is a board. So
Hmm.
it has to be there so that people can use it. And nowadays the engineering student, they do a lot of with the Arduino boards. Whatever first comes in the mind is the Arduino board.
Arduino, yes.
Yeah. So if somebody even makes this at mega chip, right, say somehow or similar to that, so they have to place it in the board. How they will do today, the students have learned from you, and they will be encouraged. And sometimes what happens that people think softwares have somewhere hidden landmines and bombs. If you start using that, it will blast away. No, it's not. Even what you might find that you are not successful at one go, if you give the next try, and the next try, and the next try, and the next try, and then you succeed.
Yes, definitely, sir. I mean, designing that
it is
PCB
it is it
board.
is I'm speaking to Swastik, I'm speaking to the audience.
Okay,
So
sir. Okay.
yeah, so students, you today saw that Swastik has done it at his end at the software level. Now, once the board is manufactured through any of the vendor, it comes back to you, and then you have to solder the different components, peripherals, etc., and then you can have a testing with that. So today we had a very, very great episode with Swastik, and the energy that Swastik has, I appreciate it, and I would like to spread the energy to the community, to the students who are enthusiastic about the microelectronic industry. And thank you, Swastik, for presenting your journey with the creation of the PCB of the at mega chip, that is the microcontroller, right? And along with explaining different peripherals. So you have something to say to the audience?
Yes, sir. I mean, like, just like I was saying before, and just like you said, sir, peer-to-peer communication. So I would suggest all of my friends who are watching this from any part of the world, I would suggest them to take up careers in VLSI industry, because frankly speaking, sir, once we get the hang of it, this is really a very, very interesting branch of study. People may think that it has got a lot of hectic tasks to do, but no, that is not the case over here. Once you get into it, sir, it is extremely interesting and extremely beautiful field of study. So I would suggest all of my friends and everyone who is watching this to take up their careers in VLSI industry, or maybe in microelectronics industry, in IoT, whatever they feel like, whatever their niche is. So don't give up on the VLSI industry. The world needs VLSI engineers.
That's a good message to your peers, because again, I will again say that there should be a belief from the students. If he can, we can. So you see the students in learn from one student is sharing their journey, the other students are learning from them, and it's a value chain that is getting created over the entire student network, maybe in India, maybe abroad, because in the global world of internet, we do not have any boundaries. So this video can be watched somewhere maybe from Middle East, somewhere maybe from the Far East or the Far West, and even our land in India. So students, please be encouraged, because this webinar series where we promote the peer-to-peer learning, and you get a chance, a live chance of interaction with the person who has done a particular project, and the project has the importance in the entire VLSI ecosystem chain, because the VLSI is unlike softwares. Because softwares, we have one software that is all in one, but in VLSI and microelectronics industry, there is a chain of events and companies. They have to proper work hand in hand to give a product to market, and each different steps or different parts of this ecosystem is equally important. So thank you, Swastik, for presenting this particular nice journey of the PCB of the IoT board. And nowadays, the Arduino board and these RISC-V boards, these are very, very hotcakes among the students. And you showed a way how to manufacture this board in the software level, obviously, and then it will go to the PCB company. So that was a great journey. Hope students have learned a lot of things. And obviously, this webinar is different from regular webinars. That means this is live. Also, later on, once we have stopped the live streaming, you can watch it, the replays, any number of times you want. So thank you, audience. And we don't have much of the inquisitive questions today. So we'll be closing the session. Thank you for waiting patiently. We'll meet in another interesting episode of the semiconductor webinar. And here I'd like to say the semiconductor webinar, as it is designed not only for the students, but professionals will also be taking part in this slowly and in pipeline, so that you get more and more out of this particular webinar. And the knowledge sharing is open. That means knowledge is open. So thank you, Swastik, for being here, and thank you, audience, for listening and watching us patiently. So we'll end the stream right now, and see you in the next episode of the Semiconductor Podcast or the Semiconductor Webinar, whichever is coming next. So bye for today.